Today, we tackle a common problem, finding the intersection of multiple arrays. Specifically, we're looking for elements that appear in all three given sorted arrays. Can you find a way to do this without iterating endlessly? The problem asks us to find all distinct integers that are present in all three input arrays. Each array is guaranteed to be sorted in strictly increasing order. The output should also be a sorted list of these common integers. For example, given arrays 1, 2, and 3, we need to return a new array containing only the numbers found in all of them. A straightforward but inefficient approach uses hash sets. Convert all three arrays into hash sets. Then, iterate through the elements of the first set. For each element, check if it exists in both the second and third hash sets. If it does, add it to our result list. Finally, sort this result list. While hash set lookups are average constant time, creating three sets and then checking against them, plus a final sort, leads to a time complexity of big O of n log n, linearithmic time due to sorting, and big O of n space for the sets. The key insight here is that the arrays are sorted. This allows us to use a three-pointer approach, similar to merging sorted lists. We'll maintain 3 pointers, one for each array, all initialized to their respective start. In each step, we compare the elements pointed to by all 3 pointers. If they are all equal, we've found a common element, so we add it to our result and advance all 3 pointers. If they are not equal, we need to advance the pointer pointing to the smallest element. Why? Because if element A is smaller than B and C, A cannot be in the intersection, so we must move past it to find a potential match. We repeat this until any pointer goes out of bounds. This eliminates the need for hash sets and sorting the final result. Let's trace this with an example. Arrays 1, 2, 3. Pointers start at index 0 for all point to 1. Since 1 equals 1 equals 1, we add 1 to our result and advance all pointers. Now array 1 has 2, array 2 has 2, array 3 has 3. The smallest is 2 in arrays 1 and 2. We advance pointers for array 1 and 2. Now array 1 has 3, array 2 has 5, array 3 has 3. Smallest is 3 in arrays 1 and 3. Advance those pointers. Array 1 has 4, array 2 has 5, array 3 has 4. Smallest is 4. Advance pointers for array 1 and 3. Now all 3 pointers are at 5. 5 equals 5 equals 5. Add 5 to result, advance all pointers. Array 1 has nothing left. The loop terminates. The final result for our example is 1 and 5. This is correct because 1 and 5 are the only numbers present in all 3 input arrays. The array is naturally sorted due to our pointer advancement strategy. You'll spot this pattern whenever you're dealing with multiple sorted arrays or lists and need to find common elements or merge them. The presence of sorted input is the biggest signal to consider a multi-pointer approach to avoid extra sorting or hash set overhead. This optimal solution runs in big O of n time, where n is the total number of elements across all arrays. Space complexity is big O of n for the result list in the worst case. This multi-pointer technique is incredibly useful. Try applying this same pattern to other problems involving sorted data. Don't forget to like and subscribe for more DSA insights.